This third film on optical systems is about transmission media, and it's basically about fiber optics. And why you use fiber optics? Well, first of all, it's less prone to noise, less prone to damping, and less prone to dispersion. Noise is the addition of extra power that compared to the signal you sent out. Damping is when the amplitude is reduced, and dispersion is when the original pulse widens and might meet a neighboring pulse, so the two may become one, and it's difficult to distinguish the logical 1 from the logical 0, the logical high from the logical low. And it doesn't carry any electrical power, which means that it's safe to use in hazardous areas like explosive areas and so on. And it's not sensitive to EMI and RFI, electromagnetic interference and radio frequency interference. So you see here the picture of a fiber alongside power cables in a subsea umbilical. And the signal here is carried perfectly well alongside those highly noisy power cables here. If this was a copper cable carrying information, the information here would be destroyed by the field, the electrical field or the magnetic field from the power lines here. Also, it's very difficult to perform tapping to eavesdropping from optical fibers, and they are really lightweight, so you can and very small, the fibers there. How does it work? You actually use total internal reflection to guide the light. So you send the light at a given angle, and the interface between the inner core and the cladding becomes a perfect mirror. If you see here, the core and cladding, they are both made of glass with different refractive indexes, but you have a higher refractive index in the core compared to the cladding. Then you have coating and fibers and jacket and so on in order to protect the fiber. What they've done here in this figure is for illustration purposes only. It's not possible to dismantle the core from the cladding. They are melted together, melted glass, which has of course been cooled down. So it's important not to send in the light at an angle that is too high, like the yellow one here, because then the light will escape into the cladding, which is also made of glass, but then finally into the coating, and it will be absorbed in the coating. Fiber limitations, you have basically three that I mentioned. Noise, which you can imagine that it is close to 0. Then you have dispersion and damping. Dispersion limits the bit rate and the segment length, and so does the other two. So either you have to have a shorter segment, or you have to go down in your bit rate if you have too much noise, dispersion and damping. First of all, let's look at dispersion. Dispersion is when the pulse you have originally widens in the time plane, and two neighboring pulses melt into each other, and it becomes difficult to distinguish a logical 1 from a logical 0, difficult to distinguish one pulse from the other. And the problem arises, the modal dispersion arises when you have a rather wide optical fiber, which allows the light beam to follow different paths through the fiber. So one ray may go straight forward, one goes from side to side, and of course the one that goes from side to side has a longer distance to go and will use longer time. So it will arrive at the receiving side later than the one that went straight forward. So therefore you get a widening of the pulse. What you can do is that you can use something called a single mode fiber, which only allows for one ray here. while this is the multimode fiber. The multimode fiber is still used for short range applications up to a few hundred meters, while a single mode fiber is used for long range up to maybe 10 kilometers. What you have to imagine here is that the ray of light is actually a wave, and this single mode allows for one wave to go through. If you have stronger light, you don't have a wave with higher amplitude, you simply have more photons. So more photons with the same amplitude, and the amplitude is about 9 micrometers, 8 to 9 micrometers. So if the core of the fiber is about 8 to 9 micrometers, that will only allow one beam to go through the light, through the fiber, and therefore you avoid the modal dispersion. Chromatic dispersion is when you have a light that is a mix of wavelengths. And this is an album cover from Pink Floyd's Dark Side of the Moon. It shows a prism, and it shows that the different colors in the white light into the prism, the different colors, they see different refractive indexes in the prism. So since the red light here sees the lowest refractive index and the purple light sees the highest, you also have to imagine that the purple light will actually go a bit slower in the prism compared to the red light. So if I send a row of different colored pulses through a fiber at the receiving side, the red one will go faster than the purple. And if I have a high data rate with pulses close to each other, they will melt into each other, where the purple light mixes with the red light from the last wave, and so on. So how do you avoid that? How do you avoid this kind of dispersion? Well, simply by using so-called monochromatic light. That is light with only one wavelength, which is the laser. So that's why you use laser sources when you send light pulses through a fiber. You also have something called polarization mode dispersion, which is that since glass is a crystal, the glass actually has a different refractive index for waves that go in one direction compared to waves that are pulsating in another direction. So therefore, this one here may the beam that goes with waves in the horizontal plane may, for example, experience a higher refractive index. Hence, they will travel slower down the fiber compared to the ones that have a vertical amplitude. Attenuation comes from two reasons: absorption and scattering. When you send light through a fiber, it will meet impurities in the fiber, and some of the impurities will absorb the photon, some will scatter the photon, which means that it will send the photon out in another direction. So it's more like the impurity here becomes a mirror to the photon. And you see here, you have three actually phenomenon reasons here. You have something called Rayleigh scattering, which is the blue curve. You have something called ultraviolet absorption, and then you have the green ones here, which are OH minus, or what I usually call water problems, water absorption. So you see the sum of the three results in this red curve here, and the best wavelengths are actually here. So if you can make light which has this color and send it through the fiber, that's where you have as little loss of power as possible and as little scattering as possible, where the light is sent back to the source maybe. But in the beginning, in the childhood of fibers, they were not able to create lasers with this color, so they had to try to create lasers which had these wavelengths. But now we have lasers with this high wavelength there, which also results in the minimal absorption of light. Here are some examples of fibers. With single mode fibers, the core is 8 to 9 micrometers, while the cladding is 125 micrometers. Multi-mode, 200 to 40 compared to each other. And then you have something called a plastic fiber, and that's what you find in audio systems, for example Toslink. And you also find it in cars and in aviation, where you have short links, but you have some vibration and such, which will introduce a problem to the glass-based single mode and multi-mode fibers. Here you have the loss here is about 0.4 to 0.25 decibels per kilometer. This one is 10 times higher, and this one is 250 times higher than that again, because it's decibels per meter. And this is used for telecom. This is for short LANs, like local area networks, so networks inside buildings and so on. This one, cars, aviation, and short links in household electronics.